Let's jump right into this explainer. Today, we're bridging shapes and algebra, focusing on the math of circles and lines. We're going to discover exactly how simple, everyday physical shapes elegantly translate into the abstract world of mathematical equations. We'll be exploring the hidden logic behind the curves and lines that literally make up our world. So if you've ever wondered how a basic geometric shape actually transforms into an algebraic formula, well, you're definitely in the right place. Let's kick things off with the physical visual we're all pretty familiar with. A simple compass, anchored at a center point, dragging a pencil to draw a perfect circle on graph paper. Just think about the actual mechanics of this for a second. The metal spike stays perfectly still, right? And the pencil sweeps all the way around it. No matter where that pencil is on the paper, the physical distance between the spike and the lead absolutely never changes. And this brilliantly illustrates what mathematicians define as a locus. Now, I know locus might sound like a super complex, intimidating term, but it really just grounds a physical drawing into a strict mathematical rule. It's simply the path of a point moving at a constant distance from a fixed point. That fixed point, we just call it the center. That constant distance, that's the radius. So a locus is really just the mathematical trail left behind by following that one rule perfectly. Okay, let's move over to the coordinate plane and see how this all builds when we place the fixed center of our compass right at the origin of a graph, exactly at 0, 0. Suddenly, that blank physical paper has an x and a y axis. The sweeping pencil is now passing through an infinite number of x and y coordinates. Our constant radius is now a straight mathematical line connecting the origin to literally any given point on that beautifully round perimeter. So here is the absolute crucial takeaway. We don't have to memorize complex standalone formulas here. By just logically mapping the physical gap of the compass using the standard distance formula, the algebra practically builds itself step by step. Since finding the distance from 0, 0 to any x and y is essentially just finding the hypotenuse of a right triangle, we just square both sides to strip away that messy square root. And what are we left with? The stunningly simple standard equation of a circle, x squared plus y squared equals r squared. It is literally just the Pythagorean theorem in disguise. No way, right? Now, things get really interesting and visually obvious when we shift the circle away from the origin. If we pick up our compass and move its spike to a completely new random center point on the graph, let's call those new coordinates h and k, the equation simply absorbs those new coordinates. Instead of just plain old x squared, we measure the difference from our new center, x minus h squared. Notice how the radius remains the exact same constant physical distance. Your compass hasn't changed its width at all, but our starting point has moved, which alters the algebra. So, this new equation, x minus h squared plus y minus k squared equals r squared, perfectly captures our new location without losing that fundamental rule of the locus we talked about earlier. But wait, what if we don't know the center point at all? What if we only know the two extreme endpoints of a circle's diameter? Believe it or not, we can actually derive the whole equation using just those endpoints, thanks to a really ancient geometric rule. If you draw a triangle inside a circle using the diameter as the base, the angle reaching up to touch the semicircle is always, without fail, exactly 90 degrees. Because those inscribed lines forming that 90-degree angle are perfectly perpendicular, their algebraic slopes have a very special, specific relationship. When you multiply the slope of the first line by the slope of the second line, the result is always exactly -1. By substituting our slope formulas into that simple rule, the math naturally unfolds into a highly useful diameter equation. It completely bypasses the need to find the center or the radius first. It's a total game changer. Now, if you take these specific scenarios and expand all the algebra out, you get what we call the general form of a circle equation. Think of this as a mathematical master key for decoding the properties of any circle you might encounter. You'll notice some dead giveaways. The highest power of x and y is always 2, and their coefficients absolutely must be equal. So if you're ever handed a long, messy equation formatted like this, don't panic. You can instantly extract the center and the radius by just applying these straightforward formulas for g, f, and c. Moving on to our next section, the angle of intersection, mathematical protractor. Let's pivot slightly from curves to straight paths and look at the geometry of intersecting lines. Because, as we'll see, algebra doesn't just draw shapes, it measures the exact interactions between them. When two straight lines cross on a graph, they form both acute and obtuse angles. And here's the cool part. We can use their slopes, m1 and m2, as a literal mathematical protractor to calculate the exact angle without drawing a single thing. By plugging the two slopes into this tangent formula, we smoothly bridge the gap between simple linear algebra and trigonometry. Navigating these types of problems is really just a matter of structured scaffolding. You don't want to try to solve the whole thing at once. You simply find your individual slopes first, using the change in y over the change in x. Once you have your m1 and m2, the rest just falls neatly right into place within the formula. It is a highly repeatable recipe for finding the angle of intersection every single time. Let's actually put this into practice to see how it works. By cleanly mapping out the coordinates of points P, Q, and R, we systematically expose the slopes. For line segment PQ, the math yields a slope of 1/2. For segment QR, we get 7/4. When we drop those two precise values into our tangent formula, it simplifies beautifully down to plus or minus 2/3. With just a handful of coordinate points, we have perfectly mapped the exact angular collision of two lines. To wrap up this explainer, I want to leave you with a bit of a challenge to really test your new understanding. We know that when a circle touches both axes in the first quadrant, its center, hk, is equal to its radius, right? But how do those h and k values react algebraically when that same circle is pinned against both axes over in the negative spaces of the second, third, or fourth quadrants? Think about how the signs would flip and how that fundamentally transforms the equation. It's a fantastic puzzle to lock in everything we've covered today, so what do you think?